Math 2414, volumes. Volume of the solid of a revolution. The disk method, example 2. Now, if you just look at the words, you might think it's the exact same instructions, except it's not. Find the volume of the solid obtained by rotating the following lamina around the y-axis. So we're going this way. So we're taking this thing and spinning it around, and it'll kind of make a top shape, if you will. So why is going around the y-axis a big deal? Well, it's not really a big deal, but it is enough of a difference to make us go, wait a second, now what? Well, first off, let's sketch where the solid is. If I were to rotate this around the y-axis, it would wind up over here, and we would get this solid. And we want to know what its volume is. Could we do this by picking a point on the x-axis and chopping it? Well, we could, but I'm not going to for a couple of reasons. Number one, we haven't built the technique yet. And number two, we're not rotating around the x-axis. What I literally just erased about finding the volume of a solid, knowing the area of a cross-section, works for both x's and y's. So in other words, if we had a function that said, tell me where on the y-axis to cut, and I'll give you the area of the cross-section, then the volume would be the integral from whatever the lowest y to the highest y is, which in this case would be bottom to top, of that area dy. So what we can do for x's, we do for y's. And since we're going around the y-axis, maybe it's a good idea to try that. But if we're going to take a point on the y-axis and cut this solid, then we need to cut it horizontally, not vertically. So let's pick a point on the y-axis. We'll put it right here. And let's cut across here and think about the shape that we would get. Well, if it's a solid of revolution and one of the axis of revolution is one of its boundaries, then you're going to get a disk. You're going to get a circle when you rotate it. So we've got this circle here, and we need to know what its radius is. Now let's think about this. Since we're cutting on the y-axis, we're going to do a dy integral. So we need to know what this radius is. We need to know the radius as a function of y. Well, what do we know about this radius? Besides the fact that it's sitting right there. We know, well, I know the ordered pair here. The trick to most of these what's the radius questions, the trick to most of these what's the radius questions is to locate a point on the boundary that involves the radius. In this case, this point on the bottom boundary or the right boundary, depending upon your perspective, involves the radius. Move this equation over. What would this point be? Would the radius be the x or the y coordinate? Well, since it's the horizontal displacement, it would actually be the x coordinate. But what would this point's y coordinate be? Well, it's this y that we cut on the y-axis. So the point on the boundary involving the radius is r comma y. Remember, y is representing the point on the y-axis where we slice this solid. Now I need an equation that relates the two, but since this point is on this graph, then it has to satisfy this equation. So this point goes into this equation, and we get y equals the square root of r, because the r is the x coordinate. Is that what we want? Well, not quite. Because we want the radius as a function of y. Because remember, what we're really looking for is the area of that cross-section. The area of that circle when we slice it, and I hold up the solid for you to look at. And the area would be pi r squared, whatever the r is. But we need to know what the radius is as a function of y. In other words, I need to know what r equals so I can replace it, and what I know is this. How would we make that say r equals? Just square both sides. This implies that y squared is equal to r. I now know what the radius is in terms of y. So I can go back to my area and replace the radius with what it equals. There's the square on the radius, but the radius is equal to y squared. So we have pi times y squared, which is pi times y to the fourth. And that's the function that says, tell me the y coordinate at which you're going to slice this solid and show me a circle, and I'll tell you what the area of that circle is. So we can find the volume. The volume is going to be the integral of the area, integral of pi y to the fourth dy, from the bottom to the top. Remember, we're measuring y's. The bottom y is 0, the top y is 2. Now it's calculus 1 problem. Antiderivative is 1/5 pi y to the fifth. Evaluated from 0 to 2. We substitute 2 to the fifth power is 32, times 1/5 is 32 fifths. Minus, if we substitute 0, well, that annihilates the antiderivative, so our volume is 32 fifths pi. You're going to see a lot of variations on this thing. Where are you cutting it? What's the area of that cross section based on where you cut it? Now integrate that. This is the disk method in disguise. The disk method said if you wanted to find the volume, integrate pi times the square of the function. The reason it's in disguise is because this is not written x as a function of y, this is written y as a function of x. If I had solved this for x and got x equals y squared, that's x as a function of y. So we could use the disk method again that just says integrate pi times the square of this, which is pretty much what we did anyway. All right, so just keep in mind, you want to take a slice perpendicular to the axis of rotation, if you can. In this case, the axis of rotation was the y-axis, so we slice perpendicular to that. Look at the cross-section. If it's a solid of rotation, it will be a circle. Locate the radius. Do what you need to do to get the radius in terms of the correct variable of integration, which in this case was a function of y. Then find the area of that cross-section, integrate it, and you got your volume. This is an easy something to follow. It's a little tricky something to set up on your own, but I've got a few more in store for you.